Hello everyone, and welcome to this video titled Implicit Differentiation. So in this video, I'm going to be taking you through a preview version of a Knewton Alta Homework Assignment that is also titled Implicit Differentiation. So please understand that this is going to be a preview version of the assignment. So the questions that I work on in this video may not be the exact same questions that you work on when you are working through the assignment yourself. But the objectives are the same, and the methods and techniques I use should be the same that you should be using. So hopefully watching this here helps you in some way when you work on it yourself. Okay, so here we are at Knewton Alta in a preview of the assignment called Implicit Differentiation. For this particular version of the course, this is section 3.8. In the upper right-hand corner, you can see a mastery bar that shows you how far along you've gotten in the assignment. Next to that, an activity log, which shows you all the different objectives the questions on the assignment will pertain to. So here there are 4 objectives, all under the heading of implicit differentiation. Pardon me. You then have a current objective, a question beneath it related to that objective, and then at the bottom of every question, you should see a feedback button. So if you're seeing any problems with the question or the answer explanations after a question, click on this feedback and you can send your issue directly to Knewton Support, and hopefully they get back to you relatively quickly and help you fix whatever issue you may have. You, of course, will not have this instructor cheat button, right? This is for instructors only, and I won't be using it for this video. You will see, however, this more instruction button. So if you're working on a question in a particular objective that you don't really remember the material all too well for, I'd suggest clicking on more instruction, and then open the instruction up, and you'll be given some reading to do or videos to watch or both that will hopefully help you get through that part of the assignment. All right. So the objective I'm given here for this first question is use implicit differentiation to find a second derivative. Okay, so I'll start off writing the equation here for, we're given the equation of some curve. Okay, so this is a curve on the xy plane, defined by the following equation. -9 times x squared, -5 times y squared equals -3. Now you can probably tell that the graph of this curve would be an ellipse. Now what I'm about to do, you don't have to do. I'm just going to put this in a standard form for an ellipse. If you've taken a pre-calculus or algebra course where they talked about the conic sections, and you might recognize this if I multiplied everything, or if I divided everything here by -3. we'd have, positive 3x squared and plus, 5/3 y squared equals 1, and then rewriting this in the standard form for an ellipse, this is x squared divided by 1/3 plus, and then the second term is y squared, divided by 3/5, right, times 5/3 divided by 3/5 equals 1. Right? That's the only reason I wanted to do this, is so you could recognize, hey, I've got an ellipse. Right, and I'll show you that picture as well. Right, here's that free online graphing calculator site, desmos.com, right? So I'm given this equation with the x and y involved, negative 9x squared, minus 5y squared equals negative 3. I told you, right? There's your ellipse, right? There's the curve defined by that equation. So we're asked to find an expression not only for the first derivative of this curve, right, the slope of the tangent line at any point, but the objective title here is find an expression for the second derivative, right? So the derivative of this curve at any point. Now remember, second derivative talked about how the curve is curving, is it the concavity of the curve. So on the top half here, see how it's curving downward, opening downward. Remember, if something was curving or curling downward like this, you had a negative second derivative at these points. Whereas down here, where the curve is curving upward, opening upward, remember concave up, curving up, the second derivative would be a positive value, right, pulled upward. But still, we're asked to take our equation, find the second derivative. Now, the title of this section, this assignment, is Implicit Differentiation, right? Because the way things look right now, so you see y is not solved for in this equation. And if that's the case, we're going to say that y is just, implied to be a function of x. In fact, you can actually see if in this equation here, you could solve for y. So if I were to solve for y, so I'll say again, if we were to solve for y, we'd get the following. You would have, let's say I was to add the 5y squared. So I'd have 5y squared and then add 3. We'd have 5y squared equals, 3 minus 9x squared. Divide everything by 5. Y squared equals 3 minus 9x squared. All divided by 5. Then I take the square root, and this leads me to two possible results. One is y equals, the positive square root of this 3 minus 9x squared all over 5, or y equals, negative square root of this 3 minus 9x squared, all over 5. And what I have down here, when y is solved for, then they say y is an explicit function of x, right, is explicitly defined as opposed to implicitly. So here, say y is f1 of x, right, some function of x f1, or y is, this other function of x, this other expression depending on x, say f2. And if you put these together, you would get the entire ellipse, and I'll show you that too on Desmos. So look, there's the original curve, the way it was originally given to us, where y was not solved for. Then I go and solve for y. So again, one of them is y equals the positive square root of 3 minus 9x squared, and then all divided by 5 in here. And you see how, I'll turn this off and on, you see how that's just giving me the top half of the ellipse? All right, so this ellipse, right, the original equation, I can break it into functions, pieces that are functions, right? Because if you look at the ellipse on its own, there are values of x that give me, multiple values of y, so they would say that y wasn't a function of x here. But you can break it into pieces that are functions. So there's the top half, and then I'll just copy and paste this and throw the negative square root, right, the other piece, and there's the bottom half, right, that green piece. This is the bottom half. So putting them together, right, give me the entire curve that we were given initially. Still, I want to find the first derivative and then, of course, the second derivative at any point, whether it be on the top half of this ellipse or the bottom half. Now, you can do this. The problem is, so you can find y, get y in terms of x. The only issue is sometimes this is difficult to do, if not impossible. Actually solving for y, getting y as a specific function of x or specific functions of x, and then, from here I could go take the first derivative, take the second derivative, but it would, be for each one separately. This is tough to do. This equation here, it wasn't so hard, right? Solving for y wasn't so difficult here, but you'll see, we may come across other curves where solving for y is difficult. So what we do, so this process of implicit differentiation is you keep the equation the way it was. So I'm going to keep this negative 9x squared minus 5y squared equals negative 3. And then you just take the derivative, you differentiate both sides with respect to, now here the input variable is called x, right? Y is implied to be a function of x. So my input is x, my independent variable is x. So you differentiate both sides with respect to the independent variable, which here is, called x. And just recall that y, whenever you see something that doesn't have x, y is implied to be a function of x, right? Like why is this square root of 3 minus 9x squared over 5, or this negative square root of 3 minus 9x squared over 5? Y represents, y is there in place of some expression involving x. So I'll take this to another page and say we could do this. So we could think of this way. The equation for our curve we could think of as -9 times x squared minus 5 times, and then y is some function of x, right? Say f of x squared equals, -3. And then from here, we differentiate. I'm just going to write diff both sides with respect to, and you've seen me do this in other videos, WRT for with respect to the independent variable x. So any term, any part of the expression on either side that involves just x itself, you treat like your typical function of x. -9 times x squared. The derivative of that, you would use the power rule for, would be -18 x to the first. Then we have -5 times, and then when I'm looking at this, right, the y squared, again, y is implied to be some expression with x in it. So it's some function of x, square root of 3 minus 9x squared over 5. Some expression with x in it, squared. So when I differentiate this, I'm going to have to apply the chain rule, right? It would be, this is a composite function. This is like having a square with this function of x put inside it. So I do, 2 times this function of x to the first power, but then, chain rule, multiply by the derivative of the expression inside, right, times f prime of x. All right, so that's the left side. And then the right side is a constant, right? The derivative of a constant with respect to any variable is 0. And then we take this here and, solve for our derivative, f prime. So here I would add 18x. So we'd have -10, this term here, this would be -10 times f of x times our f prime of x equals, and then I'd be adding 18x to the other side. 0 plus 18x is 18x. And then to get f prime alone, I'm dividing both sides by -10 times f of x. So our first derivative, okay, f prime, the slopes of tangent lines to any point on this ellipse will be, negative 18x divided by, 10 times f of x, which if you simplify things, 18 over 10 is 9/5. So this is -9x in the numerator and 5 times f of x in the denominator, where f of x, remember that's what y was, right? Y is this function of x. So we get -9x divided by, 5y, which, if you want to call f prime y prime, you can, right? So y prime or dy over dx, right? The slopes of tangent lines to any point on this ellipse, on the curve represented by this equation, is -9 times x divided by 5 times y. So notice here, though, that to find my derivative, to state the slope of a tangent line, we need to know both the x coordinate and y coordinate. And that'll happen quite often here when we're doing implicit differentiation, leaving the equation the way it is and don't solve for y. This will happen quite often where when you find your y prime, find your derivative, you need to know both the value of x and the value of y. So you need to know both x and y coordinates of, whatever point you're at. Now, this is all well and good. You can do this if you wish. Just, remember y in some equation with x and y, you can say y is implied to be a function of x, call it f of x or g of x or something of x, and then go through and differentiate both sides with respect to x and solve for f prime. That's all well and good. It's just quite often though, just to save on writing, I'll leave it as y. So rather than do all that, I would rather just leave it as y. So you got -9 times x squared minus 5 times y squared equals -3. And then, do the same thing I was doing earlier, differentiate both sides with respect to the independent variable x. And first term has just x's in it, so -18x. Then the second term has, this y variable. Again, y is some function of x, something with x's in it, and it's being squared. So I need to do the chain rule here. So again, this will be -5 times, and the derivative of this, y squared term would be 2 times y to the first, but then times the derivative of the expression inside this y, so y prime, and then equals 0. Again, the derivative of a constant on the other side. And we solve for y prime. Y prime, or dy over dx, would be the -9x over 5y. Like I told you earlier, you add 18x, divide by -10y, and simplify. All right, so this gives us the first derivative, right, which again would tell us slopes of tangent lines to our curve. And you can kind of see how this matches the graph too, right? See how if x and y have the same sign, so where x and y are both positive or x and y are both negative, so quadrant 1 points, quadrant 3 points, the slope would be negative. You have the negative out front here. And look, you go back to the ellipse. See how points in quadrant 1, where x and y are both positive, definitely would have a negatively sloped tangent line. Points in quadrant 3, where x and y are both negative, have negative, a negatively sloped tangent line. The curve is going downward at those moments. And then if x and y have opposite signs, right? So x over y would be negative. Well, negative times a negative out front here would make this positive. So you'd have positive slopes in quadrants 2 and 4. And on the graph of the curve, right, quadrant 2 points up here, you see that if you were to draw the tangent lines at these points, you'd have a positively sloped tangent. Same thing down here with the quadrant 4 points, where the x and y have opposite signs, have a positively sloped tangent, right? So this expression perfectly defines the slopes of the tangent lines to our ellipse. Now we just do it again, right? Because they're asking us for an expression for the second derivative. Right, so just solve for y prime, do the first derivative like we did here, and then do it again. Implicitly differentiate again. Okay, so y prime, so this I've got the first derivative here. So now we have y prime equals, again, now I have a fraction. So I'm going to have to go through the quotient rule. I'm going to have to go through the quotient rule here when I take the next derivative. But once again, I'm differentiating both sides with respect to x. So left side, the derivative of y prime would be y, double prime. And then let me get this paper up underneath here. And then over here, I'll call my numerator negative 9x, denominator 5y. Remember though, y is a function of x. Y is representing some expression with x in it. Y is implied to be a function of x, however you want to say that. But numerator negative 9x, denominator 5y. So remember the quotient rule, put in my denominator, so 5 times y, times the derivative of the numerator with respect to x. Now the derivative of negative 9x, treat like normal, would just be negative 9. And then minus, and then the numerator, leave the way it was, negative 9x, then times the derivative of the denominator, which would be 5 times, the derivative of y with respect to x, 5 times y prime. So 5y prime there, and then all that divided by the denominator, so 5y squared. Now they're going to ask me to simplify this. Right? This is perfectly good, but you're going to be asked to express this with just x and y, because right now this depends on x, y, and also y prime. All right, so if I wanted the second derivative to this curve at any particular point, I'd need to know the x coordinate, the y coordinate, but also the first derivative. So we're going to have to make a substitution and express in terms of just x and y. Just x and y, no y prime. Well, we already have an expression with just x and y for y prime, and that was this up here. Okay, so we're going to take this y prime and sub in y prime from the previous line for y prime down here. And then we'll have an expression for y double prime in terms of just x and y. So in my derivative here, after applying the quotient rule, I'll do some simplifying. This is negative 45y, then plus, negative 9x, 45 times x times, and then y prime. It'd be 45 xy prime, but again, I'm going to make this substitution. Remember, y prime at any point on this ellipse was this negative 9x over 5y. And then all that. So we'll have a complex fraction here, so I'm going to simplify this in a second. And all that divided by, 5y squared, which is 25y squared, right? 5y times 5y. Now, complex fraction, I can easily get rid of this denominator of 5y up top here by multiplying the entire numerator by 5y and do the same to the denominator, right? So that'll be distributed, right? There are multiple terms up here, and that's supposed to get rid of this 5y. Remember, simplifying complex fractions. So we got y double prime equals 5y times the negative 45y. So that'd be negative 225y squared. And then 5y times this next thing will cancel this 5y down here, right? So that's the whole point of this. So then we have minus, 9 times 45, 360, and 45, so minus 405 x squared. And then all this, divided by 5y times the 25y that squared down here is 125y cubed. So again, this is great. Okay, this is wonderful. This expression here with the negative 225y squared minus 405x squared all in the numerator and 125y cubed in the denominator. Pretty sure I'd be able to enter that. All right, but let me show you what they're probably going to probably do when you see their final answer. So look at this numerator. So notice back here, before I multiply by 5y, see how they both have both these terms up top have this 45 as a common factor. So this is, 225 is 45 times 5, and 405 is 45 times 9. So I'd have the following, y double prime equals. So I factor a 45 out from that numerator. And then we have, negative 5y squared from the first term, then minus, 45 times 9, right? 9x squared from the second term. And all that over, this 125y cubed in the denominator. And look at something hopefully familiar from the very beginning of the problem shows up here. So you see this negative 5y squared minus 9x squared. For this particular equation, if you take, see how that's just the left side of my equation here, negative 9x squared minus 5y squared. So for any point on this curve, right, this ellipse, negative 9 times the x coordinate squared minus 5 times the y coordinate squared will be negative 3. So this thing here in the parentheses is just negative 3. So I make that substitution. We'll do a little canceling. 5 goes into 45 9 times. And then 5 goes into 125, 25 times. So we have 25y cubed in the denominator. And then this negative and 9 in the numerator. And then negative 5y squared minus 9x squared again is just negative 3. So overall, like the simplest this second derivative expression could get has negative 27 in the numerator and 25y cubed in the denominator, right? And this is more than likely what they're going to have for their final answer. I already told you, and I've told you this in other videos, if they don't tell you to simplify, if they don't specifically say simplify this expression here in the bubble with the negative 225y squared minus 405x squared all over 125y cubed, that should be good. That works for this particular equation. It's just, you can simplify it much, much more, of course, if you need to. So I'll enter the simplified version. I already went down and got to that far, so I might as well enter it. So negative 27 in the numerator divided by, and then 25y cubed in the denominator. There's my expression for this, d2y over dx2, right? This y double prime, the second derivative of this particular curve at any moment. And then I hit submit. Okay. Yeah, see, that's exactly how they had it. Yeah. Now, after you submit an answer, it's going to tell you that you're correct or incorrect and give you some sort of answer explanation. I would highly recommend that you read through the answer explanations. Whether you got it right or wrong, if you got it correct, still glance through them. They may have done something in a way that you like better than the way you did it. And you might want to try that for future questions. Definitely read through these. If you got it wrong, read through carefully and see if you can figure out why you were wrong or where you made your mistakes. And hopefully you can learn from your mistakes and fix things for future questions that are similar. Okay, so moving on. All right, so now we're just going simply back to first derivative, right? Finding equation of a tangent line. Remember the first derivative gave us, slopes of tangent lines and all that. Yeah. So look, here's a curve, right? Again, an equation involving x and y. So, that'll represent some curve on the xy plane. So the curve 8x cubed plus 2y to the fourth, equals -6 is shown in the graph below in blue. So this thing here, I'll pull it up in Desmos as well. All right, so I'll just maybe copy and paste this. See if it works. Copy and paste this in Desmos. Oh, that does not work at all. Okay, so I'm going to type that out myself. 8x cubed plus 2y to the fourth equals -6. So 8x cubed plus 2y to the fourth equals -6, right? So there's, again, this curve, and you're seeing that. Now, this is another one of those where, there's loads of x values that give me more than one y value, right? It doesn't pass the vertical line test, so you wouldn't call this a function normally. But this one's another one where you could solve for y pretty easily. And one of the equation solutions, if you solve this for y, one of the solutions would give me the top half function, and then the other one would give me the bottom half function, kind of like with my ellipse example in the first example in this video. But that's not important. Right? We are not trying to solve for y. We're not being asked to solve for y, get y in terms of x explicitly. We're asked to keep it the way it is and have y be implicitly defined as a function of x, right? Y is implied to be a function of x here. And then from there, use the graph to draw the tangent line to the curve at the point -1, 1. All right, so again, I know it's in the problem, but here's the point, -1, 1, right? This is on the graph. There it is there, right? There's the point, -1, 1. And if I zoom in here, maybe you can tell that the curve, right? This curve definitely has a tangent line that would have a negative slope here, right? You zoom in closer, you can see that the curve is curving downward at that point. So after I'm done here, we find the derivative at this point, -1, 1. Hopefully we end up with a negative derivative. All right, so I'm back to some paper. Let's write this out. So the equation for the curve, we have 8 times, the x coordinate of any point cubed plus 2 times the y coordinate of any point to the fourth power should be equal to -6, right? This is for any point on the curve, this relationship holds. So again, you see the point we're given is -1 for x, 1 for y, and you can test that, make sure it works. -1 cubed is -1, so this first term would be -8. And then when y is 1, 1 to the fourth is 1, 2 times 1 is 2. -8 plus 2 is -6, right? This point is on the curve, as you already saw, right? You already saw that this point is on this graph. But now we need the slope. Remember, slope is, that dy over dx or y prime, right? The first derivative, slope of the tangent line. So again, without solving for y, I leave it the way it is. Going to differentiate both sides with respect to the independent variable, which here is, x. So first term has just x in it, so I treat it like usual. Just, that's going to be 24 8 times 3x squared, right? So 24x squared plus, and then the next term you have, 2 times, and y to the fourth here is like in the previous problem with the ellipse. Remember, y is something with x's in it. So I've got some function of x to the fourth power going on here. So when I go do the derivative, right, when I differentiate, I got to use the chain rule. It would be 4 times that thing to the third power and then times the derivative of the thing inside. But the thing inside is just called y here. So this would be 2 times and then 4y to the third, but then chain rule times, y prime. All right, so that's the left side, and then equals, and then the right side is a constant again, the derivative is 0. Then we solve this for y prime. So we have 24x squared plus, 8 times y cubed times y prime equals 0. I would, to get y prime alone, subtract 24x squared. So now I have 8y cubed times y prime equals negative 24x squared. And then divide both sides by 8y cubed here, right? That'll get y prime by itself. So y prime would be now negative 24 divided by 8 would be negative 3 in the numerator now, and then you got x squared still there. And then if I divide by this, that'll put y cubed in the denominator. So here is a little formula that tells us the first derivative, that tells us the slope of a tangent line to any point on that curve we were given. But you need to know the x coordinate, and the y coordinate, right? See how this depends on both x and y, and I have those, right? The x coordinate of our point is -1. The y coordinate of our point is 1, right? So at the point -1, 1, the first derivative here would be -3 times -1 squared, right? X was -1 divided by, and then just 1 cubed, y was 1. This ends up being -3 overall. Okay, so there's point, slope. So remember, you can put this information together, get the equation of our tangent line. So remember, I like point slope form to start. Y minus 1 equals, the slope, -3 times the quantity x minus -1 or x plus 1. And if you want, you can put this in slope-intercept form. This would be -3x and then -3, then +1, so -2. But there's our tangent line. And I'll enter this, y equals -3x minus 2. I'll put that in Desmos here. Y equals -3x minus 2. And hopefully you can see this red line that just popped up, is tangent to the curve we were given at this moment, right? And you zoom in closer and closer, that red line and purple curve get to the point where they're basically right on top of each other because they're pointing in the same direction at point -1, 1. So that's definitely a good tangent line. All right, so what I want to do in the problem, so they already had the line going through the point -1, 1. I just need to move this other black point here, the some other point on the line. Well, I know that that's y equals -3x minus 2. So 0, -2 would be the y-intercept. So there you go. And you can see that here, how this red line that's popped up here is definitely looking like it's tangent to the curve at the point -1, 1. And then we'll hit submit. Great. All right. So more of the same, right? Find the derivative of a function using implicit differentiation. So again, now this time you're just entering an expression that depends on x and y. Right. So again, this is another one where you could solve for y pretty easily. It's just you don't have to, right? You don't have to find an expression that tells you the slopes of tangent lines to the curve. So here's the equation we're given in this question. So it's 5, divided by x cubed plus, 3 times the 4th root. Right, there's a little 4 in the index here. The 4th root of y. And then on the other side, you got, equals 18. Now, I'm going to rewrite these so derivatives will be a little easier to do. Remember, 5 divided by x cubed, that's the same thing as 5 times x to the negative 3 power, right? X to the negative 3 is 1 over x cubed. Plus, and then 3 times, instead of the 4th root of y, I'm going to call that y to the 1/4 power, right? Remember, fraction powers are the same as roots. And then equals 18. Okay, so these are the same thing, right? These are not, I didn't do the derivative yet. I just rewrote the expression on the left side to make it easier to do the derivative. Okay, so now I'm going to take the equation and now I'm going to do the derivative, right? Now I'm going to differentiate both sides with respect to the independent variable x. So the first term there has just x involved, so I treat it like normal. Do the power rule, that'd be negative 15 times x to the negative 4 plus. And here we have 3 times, and then just like the other problems, this is y to the 1/4, not x. So it's something with x's in it to the 1/4 power. All right, y is implied to be some function of x, something with x's in it to the 1/4 power. So when I differentiate this, I once again have to do the chain rule, right? This would be 1/4 times that thing to the negative 3/4, right? 1/4 minus 1. And then afterwards, times the derivative of the thing inside. But, the thing inside here is called y. So we'd have 3 times 1/4. So that make this 3/4, right? 3 times 1/4 times y to the negative 3/4 power. Then after chain rule times the derivative of the expression inside times my y prime, or dy over dx if you want to write that. All right, so that takes care of the left side differentiating equals, and then again the right side is a constant. The derivative of a constant is 0. And now I would like to go through and solve for y prime. Like all the other problems so far, right? I just take get all the terms without y prime to the other side, and then, divide by everything that's not y prime to get y prime alone. So now if you don't like the fraction here, so maybe I'll do this first, where I'll multiply both sides by 4, right? Little times 4 both sides. So that'll make this negative 60, times x to the negative 4, then plus 3 times y to the negative 3/4 power, times y prime equals 0. I mean, even dividing by 3 would help too, right? Because 3 and 60 both have a common factor of 3. So I'm going to divide by 3 as well. Probably should have just multiplied by 4/3 earlier, but if I divide everything by 3, this would be negative 20 x to the negative 4th plus, and then just 1 y to the negative 3/4 power times y prime equals 0. And then I would add the 20x to the negative 4th. So you got y to the negative 3/4 power times y prime equals 20x to the negative 4, and then divide by this y to the negative 3/4 power. So y prime dy over dx, my slopes of tangent lines, my derivative formula, would be 20 times x to the negative 4 divided by y to the negative 3/4, and this is what I'll enter. Now they might be rewriting it so that the powers aren't negative, so you'd have, put the x to the positive 4th in the denominator and y to the positive 3/4 in the numerator. These would be equivalent, but I'm going to write it the way I had it. There's an expression involving, the x coordinate and y coordinate of any point on this curve that we were given, and stating the slope of the tangent line, the first derivative. All right, so dy over dx here. So again, my numerator was 20 times x raised to the negative 4 power divided by, and then y raised to the negative 3/4 power. And this should be good as long as what you type in is equivalent to their answer. Yeah, so remember how I said they were probably going to rewrite it with positive powers? That's what they did. Okay. All right, so back to that one where we're asked to use implicit differentiation to find the second derivative. So notice again, the 2's here, the second derivative, y double prime. So this is pretty similar. It's just, instead of an ellipse, got 4th powers here. This will be still pretty similar to what we saw in the very first problem from this objective in this video. Okay, so I've got, this is the equation of our curve, -2 times x to the 4th plus 7 times y to the 4th, and this should always be equal to 10 no matter what point you're at on the curve, right? So let's do the first derivative. First things first, find the first derivative. So I'm going to differentiate both sides, with respect to the independent variable x. First term here, treat like normal. It has only x involved, so that'd be -8 x cubed plus, and then you got this y to the 4th power here. Remember, I'm doing the chain rule with this. This is a function of x. Something with x is something to the 4th power. So times the 7 out here, this would be 28 y cubed, but then chain rule right afterwards times the derivative of the expression inside, so times y prime. And try to make your primes look less like ones, right? So y prime. All right, so that takes care of the left side, and again, the right side is a constant, so the derivative 0. And then I solve this for y prime. All right, so y prime, I would add 8x cubed and then divide by this 28y cubed. And we'll simplify that real quick here. 8 and 28 have a common factor of 4. This is 4 times 2. That's 4 times 7. So we have a 2x cubed in the numerator and 7y cubed in the denominator, right? So there's an expression telling me the first derivative, right? Slopes of tangent lines to whatever this curve looks like, and you can go to Desmos and check it out. But we want the second derivative, okay? So we go from here and we do it again. So I differentiate once more, with respect to x. So left side's no problem, right? The derivative of the derivative, y prime prime, that's your second derivative, y double prime. And then just like in the question I had earlier from this same objective, this is a quotient over here, a fraction. So I got to use the quotient rule. So my numerator 2x cubed, denominator 7y cubed. All right, so I'm going to apply the quotient rule here. This, up top, you got the denominator, 7y cubed, times the derivative of the numerator, which just involves x. So I would do it like normal. That'd just be 6x squared. And then minus, and then leave the numerator the way it is, right? 2x cubed times the derivative of the denominator. Now the denominator doesn't have x involved, but it has y. Remember, y is a function of x. So just like earlier with the 7y to the fourth, I'm doing the chain rule here with the 7y cubed. It'd be a 21y squared, but then times y prime. And then all that, divided by the denominator. So 7y cubed squared. Okay. So like the problem from earlier, very similar. See how this expression for my second derivative depends on the x coordinate of my point, the y coordinate of my point, but it also has y prime here. So we're going to get this in terms of just x and y. So this 2x cubed over 7y cubed that we found earlier for y prime, right, we're going to sub that in for y prime. Okay, and that's going to turn this into a complex fraction. So I'm going to leave things the way they are, maybe multiply some numbers here. So 7 times 6, that's 42. So I got 42 x squared y cubed in that first term up top. Then minus 42, right? 2 times 21 times x cubed y squared. And then times y prime. But y prime, I'm replacing y prime with this 2x cubed over 7y cubed. All right, that was y prime from earlier, and then all of that. So again, you got a complex fraction here. I'm going to keep this as 7y cubed squared for now. And then you multiply the top and bottom. Right, to get rid of this denominator of 7y cubed, and we multiply the top and the bottom by this, 7y cubed. Now up top, there's a difference, so I would have to distribute this, right, to both of these things, and we got the following. So 7y cubed, times 42x squared y cubed, that'd be 280 and 14, so 294 x squared y to the sixth, then minus, and then when you multiply this by this second part, the whole point is to get rid of the 7y cubed down here. So I'd have 84, 2 times 42, 84 x to the sixth y squared, and then divided by, and then down here you have 7y cubed, cubed, right? 7y cubed squared times another 7y cubed, so the quantity 7y cubed, cubed. And this is great, really. This should be good if you want to type it this way, as long as it involves only x and y, right? As long as it involves only x and y, it should be all right. But I'm going to do this, right? Because again, the whole point of these is for, I think the reason they're giving you these kinds of equations is so that the following happens, right? If you were to factor the numerator, so remember 294 and 84, All right, look at this, there's numerators. So you see how both of these had 42 in common here? For, the 294, that was 42 times 7. And then this 84 is 42 times 2. So like I'm going to pull out the common factor of 42 here. And actually, they both have 42, and they both have x squared y squared as well as a common factor. So I'll pull out 42 x squared y squared from these, and then you're left with, again, 42 times 7 was the 294. You got 7y to the fourth, then minus, and 42 times 2 was 84. And if I pull out x squared y squared, there's x to the fourth left over there. And then down here, we got 7 cubed times y to the ninth, y cubed. And after pulling out that common factor, you see this expression left over up top in the parentheses, this, 7y to the fourth minus 2x to the fourth. For this curve, that's the left side of this equation, 7y to the fourth minus 2x to the fourth. So for any point on this curve, that has a value of 10. And then we can do a little canceling. This is 7 times 6, and then one of these 7s will go away, so I'd have 7 squared down here. And, this has y squared, y to the ninth, so those two will go, and I'm left with y to the seventh. So after all the canceling and simplifying, my second derivative expression, depending on just x and y, when totally simplified, you have 6 and 10, so 60. And then there's still this x squared in the numerator, so 60x squared divided by, and then 7 squared, so 49, and then y to the seventh down here. Right? So this is as simple as that's going to get for the expression that tells me the second derivative at any point on this curve. So after all that, you got 60, 60x squared in the numerator, 49y to the seventh in the denominator, after totally simplifying, if you wish, right? Like I said, you could have typed in all that stuff with the x and y earlier, just x and y though, not y prime, and gotten the same result. All right, so another, here's a curve, the equate. Now here's one where solving for y would be either very difficult, if not impossible. It would be just really difficult. It's algebraic, but still, solving this equation for y, I would not recommend trying. Right? So, doesn't matter though, right? You don't have to solve for y. You can leave it the way it is. We're going to differentiate both sides with respect to x, and then solve for, dy over dx, or solve for y prime. And then enter that expression, right? That's all they're asking for. All right, so here's the equation of the curve we're given. Got this quantity, 2x minus 2y squared over here. Now, if you want to multiply that out, you could. You can square this expression, but I'll just leave it the way it is. And on the other side, it equals, 8x cubed plus 5y cubed. So, again, leaving things the way it is, we're going to differentiate both sides with respect to x, the independent variable x. Now, on this side here, notice it's not just x squared, it's, some expression with x. Y is also implied to be some expression with x. This is something squared over here. So I got a chain rule. So it'd be 2 times that thing to the first power, and then afterwards, times the derivative of the expression inside. The derivative of the expression inside, would be 2x has a derivative of 2, then minus, and then 2 times the derivative of y would be 2y prime. So that's just the chain rule applied to this left side. Then equals, and then right side has a couple terms. Again, the first term involves only x, so treat like normal. That would be 24x squared plus, and then y cubed here times 5. Again, the y cubed, that's something cubed, something with x's in it cubed. So I got to do the chain rule. It'd be 15y squared, then times y prime. Okay. So now I got to solve for y prime. Now there are 2 y primes here. Right, there's this inside the parentheses here, and then this term over here with the y prime. Now it's y prime to the first. Right? This is linear, they would say, in y prime, because the highest power I'm seeing on y prime is to the first power. So I remember how you solve linear equations. First, I'm going to get rid of any parentheses around the y prime. So this quantity here, I'm going to distribute to this 2 minus 2y prime, and that'll get rid of the parentheses around the y prime there. So I have 2 times this 2x minus 2y times 2, that'd be 4 times the quantity 2x minus 2y. And if you want to pull that 2 out, make it 8 times x minus y, you could. Then, minus, and then this times the next term. Again, the 2 and the 2 make 4 again. So 4 times the quantity 2x minus 2y times y prime. Okay, so that, again, that gets rid of the parentheses around the y prime over there. And then over here equals still, 24x squared plus 15y squared times y prime. So now I have a couple terms. Again, a couple terms with y prime. There's this product here, this term with y prime on the left, and this product or this term here with y prime on the right. So remember, when you're solving a linear equation for something, right here we're solving for y prime. Get all the terms with that on one side and all the terms without that on the other. So I'll take all the terms of y prime to the right and move the left ones without y prime to the left. So this term with the 4 times the quantity 2x minus 2y, that's already on the left. And then, this term, 24x squared, doesn't have y prime attached. So I'm going to subtract that, put that over here on the left side with all the other terms that don't have y prime. And then the terms on the right side will have y prime attached. So I've got the positive 15 times y squared times y prime. And then to get this term with y prime over there, right, it has a negative front. So I'm going to add it, right? So then we'll have plus 4 times this 2x minus 2y times y prime. All right, so now all the terms that have y prime attached are on one side, all the terms that don't have y prime attached are on the other. And then we're going to factor out y prime, right? That's the whole point of this setup. All right, both of these terms over here have y prime attached, right? So I'm going to factor that out, pull y prime out of both of these, and what would be left over as the other factor would be 15y squared plus, 4 times the quantity 2x minus 2y. And now if I want y prime alone, I just need to divide by this quantity, right? So we're going to divide both sides by this. So now I'll have y prime on its own. I'm just going to switch sides here, put it on the left. Y prime would be this thing, right? This side without y prime, the 4 times the quantity 2x minus 2y minus 24x squared, all of that, divided by, and then this factor that was left over, on the side with y prime after factoring y prime out. Divide by that, so that's all going to go in the denominator here, this 15y squared plus, 4 times the quantity 2x minus 2y. And if you don't like all the parentheses, you could distribute the 4 here, distribute the 4 there, get 8x minus 8y up there, and 8x minus 8y down here. But this is it. This is good. I'm going to type it the way I have it. There's your expression telling me the slopes of tangent lines to whatever this curve looks like. This little formula down here gives us the derivative, the slope of the tangent line to any point on that curve. You just need to know the x coordinate and the y coordinate of whatever point you're at. So again, back here, we're just filling this expression in. So again, make sure you put numerators with more than one term in parentheses, right? So keep it all up top. So up top, you got 4 times the quantity 2x minus 2y, and then minus the 24x squared, right? So that's all up top, divided by, and then I had 15y squared plus 4 times the quantity 2x minus 2y. That's all in the denominator, and this should be good. Just double checking that that's what I have written here, and we'll hit submit. Great. Now they might have multiplied it out. Yeah, they factored the top, multiplied out the bottom, but they got the same equivalent expression as we do. So, it's good. So another equation of a tangent line one, where like earlier. So look at this curve here. All right, I'll type this in. 5x squared plus 4y to the fourth equals negative 9xy. So look, 5x squared plus 4y to the fourth equals negative 9 times x times y. And you get in this curve here, it's like a little figure eight. I think the technical term for these is a lemniscate. Still, you got this like figure eight looking graph. All right, so any point on this curve, it's the x and y coordinates satisfy this equation. Now, one point in particular is the point negative 1, 1. All right, when x is negative 1 and y is negative 1, you're on this graph. There it is there, and I'll zoom in on that point. Now look, closely you zoom in, you can probably see that my tangent line should have a positive slope. And the curve is sloping upward at this moment. So when I go find the derivative, right, when I go find y prime here at x equals negative 1, y equals 1, I better end up with some positive slope, if everything looks like this. So let's do that. So the equation for our curve, right, you got 5x squared plus 4y to the fourth equals negative 9 times x times y. And I'm going to differentiate both sides with respect to the independent variable x. So 10x plus, and then I got to use chain rule here. This would be 16y cubed, but then times the derivative of y. All right, so times y prime. But now over on this side, see, I've got a product. There's negative 9x times y. Negative 9x times, and then y, remember, is something else with x in it that I don't know. Right? Y is some function of x here. So first factor, negative 9x, second factor, y. So remember how the product rule goes. You got, leave the first factor the way it is, times the derivative of the second factor would just be called y prime, right? It's just plain old y, so the derivative would be y prime. Then add to that the derivative of the first factor, but that would be negative 9, right? Just negative 9 times, and then leave the second factor alone. So here's the product rule applied to negative 9x times y. And then I gather all the y prime stuff to one side. So I'm going to add this 9x y prime to the left side here, and then you still have the 16 positive 16 y cubed y prime over here. And then all the terms that don't have y prime, so negative 9y, and then minus 10x, put all that on the right side. And then if you were to factor y prime out, divide by what's left, we'd get the following. So the derivative at any point for this figure 8 graph, this lemniscate, y prime would be negative 9y minus 10x in the numerator. And then again, factoring y prime out, dividing by 9x plus 16y cubed in the denominator. Now, we are at the point where x is negative 1 and y is 1, right? So I go through this and replace x with negative 1, y with positive 1, and we should get our slope. So that's negative 9 times 1 minus 10 times negative 1 in the numerator, and then 9 times negative 1 plus 16 times 1 cubed in the denominator. So the slope here is negative 9 plus 10, that's positive 1 in the numerator, and then 16, minus 9, 7 in the denominator. But it is a positive slope, right? Remember, this would be the slope at that point. And you saw in the graph I put up earlier, right? You see that the curve does curve upward at point negative 1, 1. So we do have a positive slope. So putting all this information together, our tangent line, I'll put it in point slope form first, y minus 1 equals 1/7 times the quantity x plus 1. Or if you like, putting it in slope-intercept form, y equals, 1/7 x, and then plus a 7th plus 1, that'd be plus 8/7, right? 1/7 plus 7/7. Either way, right, there's our tangent line. So when I go back to the graph in the problem, now I'll enter it here actually in Desmos just to double check y equals, 1/7 times x plus 8/7, right? And you can see this purple line that showed up here, definitely tangent to our curve at that moment, right? Pointing in the same direction. The closer you zoom into that point, the better the line and the curve get to being one another, right? They're so close to each other at that point. But yeah, so back here though, so again, they gave us the line going through negative 1, 1. We just have to move this other point, and it only goes on corners of boxes, right? These lattice points where coordinates are integers. So I gotta move this so that the slope is, positive 1/7. So I go from here, I go up 1 and then right 7. And I'd be at this point, right? If I go up 1, the y coordinate's 2, and then right 7, the point is, at 6, 2. So this is our line here with a slope of positive 1/7. That would be tangent to this curve at the point negative 1, 1. Great. All right. So again, more of the same. Here's some equation involving x and y that defines a curve on the xy plane. And we're asked to write an expression for the derivative at any point. And again, this should involve, x and y. So here's one that you definitely wouldn't be able to solve for y. That would be quite daunting. So we have y times the cosine of, and then inside the cosine here, 6x minus y. All right, so that's the left side equals, and then over here, negative 4x times y plus 7. All right, so I leave things the way they are. We'll differentiate both sides with respect to x. And there's a product rule and chain rule and all sorts of stuff going on here. So over here, I've got a product. Right, there's y first factor, and then this cosine of something for the second factor. Or I'll have to use the chain rule when I differentiate this because it's not just the cosine of x, it's the cosine of, 6x minus y. So over here, I'm doing the product rule. So first I leave the first factor alone times, and then the derivative of the cosine of something, remember, is negative sine. I'll put the negative out front here. Negative sine of that thing, but then chain rule, right, afterwards, times the derivative of the expression inside would be 6 minus y prime. All right, so that's first factor left alone times the derivative of the second factor plus, and then derivative of the first factor, well, the derivative of just plain old y would be called y prime, and then times and, leave the second factor the way it was, the cosine of 6x minus y. All right, so there's the left side with the product rule equals, and then similarly with the right side, you got negative 4x for the first factor times, and then another function of y, right? Another function of x, this y expression in the second factor, and then plus 0. But I'm doing the product rule. All right, derivative of 7 would be 0. So I'm doing the product rule again. So it'll be negative 4x, leave the first factor alone, times the derivative of the second, so times y prime, and then plus the derivative of the first factor would be negative 4 times, and then leave y alone. All right, so there's the right side. All right, and then like before, there was a problem similar to this before. I'm trying to solve for y prime. So first I want to get rid of these parentheses that are around my y prime expression. So that's going to require taking this quantity out front here and distributing it. So we have negative, negative 6y times the sine of 6x minus y. So that was the first one. And then, plus, you have negative, negative. So plus, and then y times the sine of 6x minus y times y prime. All right, so again, that gets rid of the parentheses around the y prime expression there. Then you got another y prime term, right? Plus y prime times the cosine of 6x minus y equals, and then all the stuff over here, negative 4x y prime minus 4y. All right, so like before, all the terms that have y prime attached, this term and this term and this term on the right side. I'm going to take them all to one side and factor y prime out. So let's say I put this over here. I'm gonna add 4xy prime and then factor y prime out. So we'd have y prime times. From this term, we'd have y times the sine of 6x minus y left over. Plus from this term, we'd have the cosine of 6x minus y. And then when I add this and pull y prime out, we'd have positive 4x left over. Okay, so that's all the stuff that has y prime in it on one side with y prime factored out. And then all the terms that don't have y prime, right? This term here, And this term here, I'm going to move this to the right side. So over here we'd have, positive 6y. Again, I'm adding this to the other side. 6y times the sine of 6x minus y. So that was this moved over, and then you still have this minus 4y on the right there. And then finally, taking the expression times y prime here, this whole thing, and then dividing, divide by that expression, and get y prime alone. So we would have y prime equals this, right? This 6 times y times the sine of 6x minus y minus 4y, right? This was the right side. And again, all this stuff that was left over when I factored y prime out in the denominator. Y times the sine of 6x minus y plus the cosine of 6x minus y, and then plus 4x. So this here is what I'm going to be typing in. Doesn't really simplify in any other way I see. So it's a lot involved there with the product rules. So I got my numerator, 6y times the sine of 6x minus y, and then minus 4y. And then in the denominator, y times the sine of 6x minus 4y, then after that, plus the cosine of 6x minus y, and then plus 4x. All right, so that, let me just double check. Yeah, comparing it to what I've written. Yeah, it looks like that's good for my y prime. Hooray. So we're doing this again. All right, just finding, given some equation for a crazy curve on the xy plane, and finding an expression that gives us the slopes of the tangent lines to that curve, right? Y prime or dy over dx here. Okay. So here's our curve, right? You got negative y, the opposite of y, minus 7y cubed, then minus 4x to the fourth plus 6x, then minus 2xy, and then equals 1. All right, so again, I leave this the way it is, differentiate both sides with respect to the independent variable x. So again, the opposite of y prime, y, that would just be negative, opposite of y prime. Next term, chain rule, right? It's not just y, but y cubed, so it'd be minus 21y squared times y prime. Then the next terms involve solely x, so I would treat them like normal. That'd be minus, 16x cubed plus 6. And then this last term here on the left side is a product again. You have negative 2x times y, so it'd be negative 2x times y prime, and then minus 2y, right? You saw a couple of these where it's again first term, first factor, negative 2x times the derivative of the second one, y prime, and then the plus, the derivative of negative 2x is negative 2, and then you leave the second factor y alone. So there's your product rule. All right, then on the other side, you got, 0. The derivative of a constant is 0. All right, so all the terms of y prime, this one, and this one. So I'm just going to kind of skip to the end. We got y prime equals, I would take all the terms without y prime to the right. So that'd be positive 16x cubed. All right, taking care of that one. Minus 6 and then plus 2y, right? Undoing all those, taking all those to the right. And then I would divide all this by what's left over after factoring y prime out. So if I factored y prime out of all these terms, we'd have -1 minus 21y squared, and then minus 2x, right? And this is what I would be dividing by. So there's an expression where y prime is given, right? Slopes of tangent lines to this curve, whatever this curve looks like, are given in terms of, the x and y coordinates of any point that you are at on the curve. All right, so up top, in parentheses, 16x cubed minus 6 plus 2y, and then in the denominator, -1 minus 21y squared minus 2x, and I think that's pretty much is everything I've written. Great. All right, so more of the same. This is very similar. All these problems seem to be here. So curve we're given this time is the following, right? You got the quantity, -8x minus 2y, that whole thing cubed, equals -x squared minus 10y squared. So again, this is pretty similar looking to a couple questions ago in this particular objective. So again, I want an expression for the first derivative. Once again, differentiating both sides with respect to the independent variable x. So over here, it's just, chain rule. It would be 3 times this quantity, -8x minus 2y squared. But then afterwards, times the derivative of the expression inside would be -8 minus 2y prime. All right, so that's the left side. And on the right side, -x squared, derivative would be -2x. And then chain rule here for the y squared, so it'd be minus 20y. But then afterwards times the derivative of y, right? So y prime. Again, we have this set of parentheses around the y prime thing here. So this quantity out front, this 3 times this quantity squared, I'm going to distribute that to get rid of the parentheses around my expression with y prime involved. So that'll give me -24 times the quantity -8x minus 2y squared, and then minus 6 times this -8x minus 2y squared quantity, times y prime. All right, so see now the y prime term is free. It's out of the parentheses now. And then there's nothing over here to do, so I got -2x minus 20y y prime. All right, so all the terms with y prime involved are this term on the left and this term on the right. So say I were to gather the y primes on the right. So I'd have, add 6, so it'd be +6 times this -8x minus 2y squared, and then minus 20y. That's what I'd have left over from those terms after factoring out y prime. And then the -2x here, the term without y prime, I'm going to add that to this side and get, +2x. And then I still have this other term over here without y prime, minus 24 times the quantity -8x minus 2y, squared. And then I'm dividing by this thing in the brackets here, right? So I'm dividing by this. So we'd have y prime equals this 2x minus 24 times the quantity -8x minus 2y squared. all divided by, and then this expression here, 6 times the quantity, negative 8x minus 2y squared, minus 20y. So here's what I'm typing. Again, a lot of writing to do. And I didn't even show every little step, right? A lot of writing to do with these. So again, numerator, parentheses, 2x minus 24 times the quantity, negative 8x minus 2y squared. Right, that's all in the numerator. And denominator, 6 times the quantity, negative 8x minus 2y squared, then minus 20y after that. And this should be good. Great. All right, so another one where we're just, again, this is similar to one we saw earlier with a fourth root, So, just writing this out. Yeah. So same steps every time, right? Just differentiating both sides with respect to x. Solving for y prime. So I have 3 times the fourth root of x plus 2 times y to the 2/3 power. And this should be, for any point on this curve, the x and y should make this left side equal to 75. So again, this is the same thing. I'm not doing the derivative yet. I'm just rewriting this as 3 times x to the 1/4 for right now. Plus, and then 2 times, y to the 2/3 equals 75, right? So these are just the same curve. I did not do the derivative yet, but now I'm doing the derivative. All right, so now I'm differentiating, with respect to x. So the first term here would be 3/4 times x to the negative 3/4 power, right? 1/4 minus 1 plus, and then 2 times 2/3 would be 4/3 times y to the negative 1/3. But then chain rule, right? This is some expression with x to the 2/3. So then times the derivative of y, right? So times y prime there equals 0, right? The derivative of a constant. Now, if you don't want the fractions involved, right, you multiply both sides by 12 here. That would be the least common denominator. So that's 9 times x to the negative 3/4 plus 16, right, 4/3 times 12 times y to the negative 1/3 times y prime equals 0. And then solving this for y prime, I would subtract the 9x to the negative 3/4 and then divide by the 16 y to the negative 1/3. And as we saw earlier, right, you can leave it this way with the negative powers. They might rewrite it with positive powers, but that's what I'm typing. So numerator negative 9 times x raised to the negative 3/4 power, and then divided by 16 times y to the negative 1/3 power. Great. Okay, and then back to one of those second derivative business, right? So very similar, right? You see all these terms, they both have a cube here. The first one we saw, they both were squared. The second one we saw, they were both to the 4th power, right? Very similar. So here's the curve we're given. Negative 7 times x cubed plus 5y cubed equals negative 9. I'm just going to write diff now. Differentiate with respect to x. I hope that's implied now. You should understand that. So this negative 21x squared plus 15 times y squared, but then times y prime chain rule equals 0. So y prime would be positive 21x squared divided by 15y squared. But, 21 and 15 have a common factor of 3, so that'd be 7x squared in the numerator divided by, 5y squared in the denominator. So there's y prime. And then I'm going again, right? They do want an expression for y double prime. So now the left side is y double prime, and right side I've got a quotient once again, right? Very similar to problems from earlier in this same objective. So I'm doing the quotient rule. So denominator 5y squared, derivative of the numerator 14x, minus, and then the derivative of the numerator the way it is, 7x squared. Derivative of the denominator, I'd be applying the chain rule to. This would be 10 times y, but then times y prime again, and all that divided by the denominator, squared. And we sub this 7x squared over 5y squared in for y prime here, so that our second derivative depends on only x's and y's and not y prime. So we have, 5 times 14, it's 50 and 20, so that'd be 70 times xy squared, then minus 70 times x squared y, and then y prime, right, was this 7x squared over 5y squared, and then all this divided by, 5y squared squared. As before, right, everything up top and bottom here, I'm going to multiply by this 5y squared denominator here from y prime. Multiply the top and bottom by 5y squared. That'll be distributed up here to both these terms. Okay. Some paper. So up top, 5 times 70 is 350 times x, y to the fourth. And then again, the 5y squared will go away in the second term, so I'm left with minus 490, 70 times 7, x to the fourth y. And then divided by down here, we got 5y squared, cubed. And then, like before, I told you this should be fine, right? This involves only x and y. There's a perfectly valid expression for y double prime. It's just if you were to factor this out up here, right? These both have 70 in common, and in fact, they both have 70 xy in common. And if I remove 70xy, you'll have 5y cubed in the first term, and then minus 7x cubed in the second term, and then, divided by, and I'm going to write this down here as 5 cubed times y to the sixth, right, when I cube that. And then this expression here, 5y cubed minus 7x cubed, right, for this particular equation, that's negative 9, right? This in the box here, in the brackets here, there's the left side. So this is negative 9. All right, this thing becomes negative 9. And then we do a little simplifying, right? Y up here cancels one of these y's, makes that y to the fifth. This is 5 times 14, and then one of these 5's goes away, so it becomes 5 squared. And that should be it. So 14 times negative 9, right? That's 90 and 36. So negative 126 in the numerator, with still an x as well, right? We can still got this factor of x here, and then 5 squared is 25, and then you got y to the fifth in the denominator. So this would be the totally simplified version of the second derivative involving just x and y. So in the numerator, negative 126, x, and divided by 25y cubed. Oh no, I made a mistake. oh no, y to the fifth. I wrote down y to the fifth and typed y cubed and said y cubed. This should be 25 y to the fifth down here. My apologies. All right, great. Okay, sorry, I wrote it down correctly. I just didn't type it right. Okay, and let's see. So another second derivative, right? So this should be pretty similar to the previous problem, previous couple problems, from this same objective where you're finding the second derivative. So we got 3x cubed minus 7y cubed equals negative 8. All right, so I'm going to go right into it. Derivative with respect to x, you got 9x squared minus 21y squared times y prime, chain rule, equals 0. So y prime would be, 9x squared divided by 21y squared, right? The negatives would cancel, so 9x squared divided by 21y squared, which 9 and 21 have common factor of 3. So it'd be 3x squared over 7y squared. I got another quotient here, so when I go again, right, we'll differentiate again. You got y double prime equals, and then applying the quotient rule, right, that's denominator 7y squared times the derivative of the numerator would be 6x minus, and then the numerator is 3x squared times the derivative of the denominator would be 14y times y prime. Chain rule, right? And then all that divided by the denominator, 7y squared squared. And this, again, we're rewriting this as 3x squared over 7y squared. So we got 42xy squared minus 42 times x squared y times y prime, right? This 3x squared over 7y squared. All that divided by 7y squared squared. I'm going to multiply everything up top here and the bottom here by 7y squared. To simplify this. All right, so up top, got, 280, 294 xy to the fourth minus, and then again the 7y squared will be gone in this next one when I multiply it. So you got 126, 3 times 42, 126 x to the fourth y. Down here it would just be 7y squared, cubed. But both of these had this, 42 in common. All right, so if I pull 42, they both have 42xy in fact. And if I remove that, you'd have 7y cubed minus 7y cubed there. Then minus, if I pull 42 out of this, it'd be 3x cubed. All that divided by, and again, this 7y squared cubed. All right, so this time it's a little different because look at the terms in there, in the box here. They're the opposite. See how this has positive 3x cubed minus 7y cubed? This is the other way around, negative 3x cubed plus 7y cubed. So this is positive 8, right? Instead of negative 8. So this becomes positive 8. And if I multiply some things out, again, this is 7 cubed times y to the 6th down here. So one of the y's will go away, make that y to the 5th. This is 7 times 6, so that takes care of one of these 7's, make that 7 squared. And there we go. Right? So numerator has 6x times 8, so that'll be 48x in the numerator. And then 7 squared y to the 5th, 49 y to the 5th. And again, I'll try to remember to type the 5th down here for the second derivative. So numerator 48x divided by, and then 49y to the fifth. Okay. All right, so that second derivative one is done, thank goodness. All right, so then again, we're just, I think the rest of them are similar, and then we might have a tangent line one left over. But we're given a curve and, trying to, through implicit differentiation, find y prime, the slope of the tangent lines to that curve at any given point. Okay, so the curve we're given here is the square root of x times y equals, and then over here, 1 plus x squared y cubed, x squared times y cubed. All right, so this I'm going to write as x to the half times y to the half. Okay, so it's the square root of x times square root of y, x to the half times y to the half, and we'll do the product rule over there, and then over here still got 1 plus x squared times y cubed, right? So I haven't done the derivative yet, right? I just rewrote things. Now I'm writing the derivative, diff. Product rule here, so again I leave the first the way it is, x to the half. Derivative of y to the half would be half y to the negative half, and then times y prime, and then plus, and then derivative of the first factor would be half x to the negative half, and then leave the second factor alone, right, y to the half. Right? So there's the product rule applied to the left side, equals, and then the right side, derivative of 1 is 0, and then I have another product to do, product rule, so x squared times derivative of y cubed would be 3y squared times y prime, and then plus, derivative of x squared is 2x times, leave the y cubed alone, okay. Then the terms with y prime attached, there's that term on the left and that term on the right. So if I were to gather those to one side, say I took them all to the left and then factored it out, all right, factored y prime out, we'd have the following. I'm going to take this to the right side, so we got, on the right side, we'd have 2xy cubed minus half x to the negative half times y to the half, right? Those are all the terms without y prime put on the right. And then again, I would subtract this term with the 3x squared y prime, factor y prime out and divide. You'd have this being divided by half x to the half y to the negative half from that one, and then minus 3x squared y squared. Okay, and if you don't like all the fractions, you can multiply the top and bottom by 2, make this 4 and 1 and 1 and 6. But there's our y prime expression depending on x and y. So yeah, I'll do that so I don't have to type all the fractions because I have a bunch of fraction powers here. In the numerator, if I multiplied everything by 2, it'd have 4xy cubed, then minus 1 times x to the negative half power times y to the positive 1/2 power. Yeah, that's all in the numerator divided by, and then again, I doubled everything, all the coefficients up, so you got just 1 x to the positive 1/2 power times y to the negative 1/2 power. Then minus, doubling the coefficient, minus 6x squared y squared. All right, and this should be good. Oh man. Maybe I rushed that a little too much. Okay, well, look back at my page here. That is like, I wrote xy to the half, which if I did the chain, I just kind of retooled that, see if I can work it any differently. So if I wrote the left side as xy to the half, but if I did the derivative of that, be half times xy to the negative half, and then times the derivative of the product inside. So using the product rule, it would be xy prime plus y. And if I were to distribute this using properties of exponents, I'd get what I had here. On the right side, product rule, x squared times 3y squared y prime plus 2x times y cubed. Take that away, factor y prime out. All right, so then so now I'm thinking, let's see if we rewrite these using roots. So this would be the square root of y divided by the square root of x, so square root of y over x. And this down here would be the square root of x divided by the square root of y. So you know what, I'm going to try writing this, typing this in down here, because it's the same thing. But maybe because the first equation had square root, maybe they want it this way. All right, so I'm gonna get rid of this and see if this works out. We got 2xy cubed minus 1/2 times the square root of y over x. It's all in the numerator, divided by, and then 1/2 times the square root of x over y. And then after that, after that, minus 3x squared y squared. I'm going to see if this works out. They did. Oh, well, that's not right. This is exactly equivalent to what I had earlier. This is equivalent to what I had earlier. Look, you got the 2x xy cubed minus this is 1/2. You know, this would be the square root of y over square root of x, rewritten where they multiply top and bottom with square root of y. Then down here, this is half the square root of x over square root over y minus 3x squared y squared. This is the same as what I had. All right, so I'm going to send feedback to them later about this. The expression that I have in there is correct. All right, so let's continue on. All right, do another one of these. So here's one pretty similar to one of the ones we saw earlier. So again, let me write this out. So left side we got y times the cosine of 2x minus 4y equals negative 2x y minus 4. All right, so leaving it the way it is. Differentiate. So left side's another product. So I'm going to leave y alone. And then the derivative of the cosine of something is negative sine of that thing. So you got negative, y times the sine of 2x minus 4y. But then chain rule, right, times the derivative of the expression inside would be 2 minus 4y prime. And then plus, and then the derivative of the first factor is y prime. And then leave the second factor alone times the cosine of this 2x minus 4y. Okay, so that's the left side, product rule. And then the right side, another product, right, where negative 2x times y, so it'd be negative 2x times y prime. And then, just minus 2y. So negative plus negative 2 times y. All right, and then I gotta distribute this quantity here to get rid of the parentheses around the expression with y prime here. So this would be -2 times y times the sine of 2x minus 4y, and then plus, negative times negative plus 4y times the sine of 2x minus 4y times y prime. Yeah, that gets rid of the parentheses around my y prime term. And then the rest of it's still the same, plus y prime times the cosine of 2x minus 4y. So that finishes off the left side, equals -2x times y prime minus 2y. Okay. So all the y prime terms, there's this term on the left, and then this term on the right. So again, I would move this over here. Let's say I move all the stuff with y prime to the left and factor y prime out, and then divide. All right, so I'm going to go to the end. So again, my terms without y prime, on the right side I'd have -2y, and then add this, so then plus 2 times y times the sine of 2x minus 4y. And then after adding the 2x y prime, factoring y prime out, and dividing, the denominator here would have, positive 2x and plus 4y times the sine of 2x minus 4y, and then plus the cosine 2x minus 4y, right? And this should be good. And hopefully I don't come and run across the same issue as with the last problem with those roots. Because again, I've been telling you that if you put in an expression that's equivalent to the right answer, it'll give it to you, but it didn't. It didn't in the last one. But that previous problem we saw that was similar to this with the cosine and sine seemed to work out. So I'm gonna type this one in as is. So numerator, got -2y plus 2y times the sine of 2x minus 4y, right, all in the numerator, divided by, and then 2x plus 4y times the sine of 2x minus 4y, and then plus the cosine of 2x minus 4y, all in the denominator. And that should be good. That looks like what I typed. Great. All right, so that objective's done. Once again, I'll be sending some feedback about that one problem that's really bothering me, if you can't tell, where I had an equivalent expression for what they had, but they didn't give it to me. Okay, and then we got equation of a tangent line once again. So now this one, they just want the equation, well, they just want dy dx at this point. All right, so they don't even want the equation of the tangent line. They just want you to evaluate dy over dx, y prime, right? What's the slope of the tangent line at this point, -1, 2 on the graph of this curve? So just the slope. So we have 6x to the 5th plus 6x to the 4th, or y to the 4th, sorry. That's a y. 6x to the 5th plus 6y to the 4th equals -45 times x times y. So let's differentiate both sides with respect to x like all these other ones. So that's 30 x to the 4th plus 24 y cubed, but then chain rule times y prime. And then over here I got the product rule again with -45x times y prime, and then -45, times y. solving for y prime. Again, this term has y prime on the left, this term has y prime on the right. Let's say I move that over here, and then in divide, our denominator would have 24y cubed plus 45x. And the numerator, again, I moved all the y prime stuff to the left, so this doesn't have y prime. Keep it on the right, and then move this. So I'd have negative 45y, minus 30x to the fourth. So here's an expression for y prime, and then at the point, negative 1 comma 2, and this is x, this is y on this curve, y prime, right, the dy over dx slope of the tangent line, it's going to be negative 45 times, y, so negative 45 times 2, minus 30 times x to the fourth, negative 1 to the fourth. So that'll be the numerator, and denominator 24 times y, so 24 times 2 cubed, plus 45 times x, 45 times negative 1, and we're simplifying this. So this is negative 90, and then minus 30, so negative 120 in the numerator. And then 2 cubed is 8. 8 times 24, it's 160, and 32, that's 192. But then minus 45, be 147 in the denominator. And they have a multiple of 3 in common. It's 3 times 40. And this is 3 times 49. And 120 and 27. So there, that's as simple as that would get. So there's our slope, and that's all they asked for. Right, we got the point. They asked for the slope of the tangent line. I'm putting in, they said an exact answer, so I just leave it as is, negative 40 divided by 49, right? You're not entering this into a calculator and rounding or anything. Wonderful. All right, so another one where we're asked for, here's some curve on the xy plane. We're just asked for the slope, once again, dy over dx, y prime, at a particular point. All right, so pretty similar to the last question. So here was our curve. Okay, so we differentiate with respect to x. So we got negative 15x squared minus 5 times y to the fourth, but then times y prime, chain rule, plus 8 minus 3y prime on the left side there equals 0 on the right. So this has y prime, this has y prime. So if I were to factor that out and divide, we're going to have a denominator of, negative 5y to the fourth minus 3. And the stuff without y prime, I'm going to move to the other side before I do that division. So I'd have positive 15x squared, minus 8 in the numerator. So there's our expression for, the derivative at any point on this curve. And then we're specifically at the point where x is negative 2 and y is 1. So y prime, slope of the tangent line there is going to be 15 times, negative 2 squared, the x squared, minus 8 in the numerator. Then negative 5 times, the y coordinate is 1 to the fourth power minus 3. Negative 2 squared is positive 4. 4 times 15 is 60. 60 minus 8. Got 52 in the numerator. And then 1 to the fourth is 1. Negative 5, is negative 5 there, minus 3 would be negative 8 in the denominator. So this is a negative value and these are both multiples of 4. All right, this is 4 times 13, and this is 4 times 2. All right. So negative 13 halves will be the slope. Negative 13 over 2. Great. Wonderful. All right. So from that one question aside, again, where I had an expression that was equivalent to what they had. So that one question aside, where I'll be sending feedback to Knewton about that. Hopefully watching through all these is enough to help you out in some way, give you guidance when you go about working on this on your own. Thank you very much for watching.